This example problem is asking for you to compute how much ethanol can be produced from a ton of sucrose. So for the fermentation of sucrose with water results in ethanol and carbon dioxide. So again, here you have sucrose reacting and water that reacts to yield ethanol and carbon dioxide. So to begin this analysis, let's go ahead and try to find the molecular weight of each constituent. So you have the molecular weight of carbon, which is 12.01 kilograms per kilomole. Hydrogen, which is 1.008 kilograms per kilomole. And then oxygen, which is 16 kilograms per kilomole. With that, what we're going to do now is try to find the total molecular weight of sucrose. So that'll be C12, H22, and O11. So we'll go ahead and do that. 12 times the molecular weight of carbon plus 22 times that of hydrogen plus 11 times that of oxygen. So that would give us molecular weight of 342.3 kilograms per kilomole. And we could do the same thing for ethanol, which is C2H5OH. So it would have 2 times 12.01 plus 5 times that of hydrogen plus 1 of oxygen plus 1 more hydrogen. That would give us a total molecular weight of 46.07 kilograms per kilomole. So in order to find out the total amount of ethanol, we know that for 1 mole of sucrose, there are 4 moles yielded of ethanol. So we would go 4 times the amount of ethanol per sucrose. And it's telling us that it has 1 ton of sucrose. The math would work out that we would get basically 0.538 tons or 1,077 pounds of ethanol produced by the 1 ton of sucrose. And obviously the main reason is that sucrose has a huge molecular weight as compared to ethanol. Some notes about ethanol. Although grain is a leading feedstock for ethanol production in the U.S., the significant replacement of gasoline by grain-based alcohol would be very difficult. Availability is the primary limitation. Let's give you an idea. If all the corn in the United States were used to produce ethanol, the ethanol produced would only replace about 10% of the gasoline used. So for close to 100% replacement of gasoline by ethanol, the production of corn would have to increase by a factor of 10. Let's take a brief look at methanol now. Methanol is also called wood alcohol and can be used as a fuel in modified internal combustion engines. The heating value of methanol as a fuel is nominally 76,000 BTU per gallon, or about 58% of the value of gasoline. So that's a motor that has a gas mileage of 24 miles per gallon would likely have a methanol mileage of about 14 miles per gallon. Most of the methanol in the US uses natural gas as the feedstock. So the production of methanol from natural gas involves 3 chemical processes. First, natural gas, primarily methane, reacts with steam to produce synthesis gas, carbon monoxide and hydrogen. According to this chemical reaction, so you have methane and water yielding carbon monoxide and hydrogen. In a second step, the synthesis gas is combined with carbon dioxide to alter the ratio of hydrogen and carbon monoxide. So again, you have hydrogen carbon dioxide yields water and carbon monoxide. And then for the third step, carbon monoxide and water in the presence of a catalyst are used to produce methanol. So while the production of methanol from natural gas only increases the demand for natural gas, an important observation in relation to the three-step process is that only step one, the production of synthesis gas, involves natural gas. So synthesis gas can be produced from a variety of carbonaceous biomass feedstocks, as well as coal. Methanol itself has many advantages over conventional gasoline. For example, the methanol air flame temperature is lower than that of gasoline, so the NOx production would be reduced. Methanol produces no sulfur oxides, and methanol has limited soot and CO2 emissions. So, as for drawbacks, in addition to the lower energy density we talked about earlier in regards to the methanol mileage compared to gas mileage, methanol produces severe health hazards when ingested or absorbed, and it is also soluble in water. Also, since methane burns with a nearly colorless flame, accidental emissions can be very difficult to see. And then there are some other processes as well. Biodiesel, for example, or vegetable oil. Biodiesel is a fuel composed of fatty acid alkyl esters and is made from feedstocks such as vegetable oil and animal fats. This is not a useful definition for non-chemical engineers, so we're going to look into this a little bit more. So a plethora of oils can be extracted from seeds, nuts, and other plant parts. Additionally, recycled cooking oil and animal fats are sources of biodiesel feedstocks. Excuse me. Examples of this include corn oil, linseed oil, olive oil, soybean oil, and sunflower oil. So, although these and similar plant oils can be used to fuel diesel engines, the direct use of plant oils in diesel engines shortens the operation life and leads to engine maintenance issues. So, also, plant oils have higher viscosity by a factor of about almost 20 than diesel fuel and has a lower centane number, which is a performance metric used. A study by Schober states that the expected 10,000 hours between engine overhauls can be reduced to as little as 600 hours for sunflower oil operation or 100 hours for operation on linseed oil. And then there's pyrolysis liquids. Pyrolysis liquids is defined as the thermal decomposition of organic compounds in the absence of oxygen. Charcoal is a simple example of this, and that results when wood is heated to about 250 C, and the moisture and volatile products are driven off by the heat. The resulting product has a very high carbon content. Pyrolysis is an endothermic reaction that leads to the degradation of solid fuels into a variety of gases, organic vapors, and liquids. In contrast, combustion is an exothermic reaction that involves the rapid oxidation of fuel with a large release of heat. And then there's biogas. Biogas is a mixture of methane and carbon dioxide. So it's typically 50 to 80% methane and 20 to 50% carbon dioxide by volume, with traces of hydrogen, carbon monoxide, and nitrogen. Biogas is the final product of anaerobic digestion of organic waste, such as animal manure and food processing waste. Anaerobic digestion is decomposition of such wastes into gaseous fuels by the action of bacteria in an oxygen-free environment. So biogas differs from natural gas in that natural gas is composed of more than 70% methane, with the remaining constituents being other hydrocarbons. Biogas is also regarded to as swamp gas, landfill gas, or digester gas. Biogas is produced in stages by different types of bacteria that break down the complex organic compounds. So the following four stages here with the associated bacterial function form the generally accepted path from organic waste to biogas. So you have hydrolytic bacteria break down the waste into sugars and amino acids. Fermentative bacteria convert the sugars and amino acids to organic acids. Acidogenic bacteria then convert the organic acids to hydrogen, carbon dioxide, and acetate. And then methanogenic bacteria produce biogas from the acidic acid, hydrogen, and carbon dioxide. Here's an example of a batch anaerobic digester. So in this case, anaerobic digestion takes place in an airtight chamber called a digester. So again, you have here the mixing tank. Here you have the mixture, which is called a digester, and then some sort of lagoon for the storage. And then there, last few slides here, we're going to go over, briefly describe producer gas. Producer gas is a low to medium BTU flammable gas mixture containing carbon monoxide, hydrogen, methane, nitrogen, and carbon dioxide. And also higher hydrates is made from gasification of wood or coal. And then we'll go ahead and end with this one, synthesis gas or syngas. It's a mixture of carbon monoxide and hydrogen. It can be produced by a gasification process using oxygen rather than air. So the oxygen requirement for syngas production is about 1/3 of the oxygen required for complete combustion. Synthesis gas is also named because in addition to being a useful high-energy fuel, it can be used as a feedstock for the synthesis of many useful chemicals. Syngas is produced from a process called Fischer-Tropsch to produce a wide range of hydrocarbons, typically in liquid form. So we'll go ahead and end there. The last bullet point here I had forgotten to take out. I did go over an example problem in the past, but we're going to forego that in this case. Okay, well, thank you very much. This slide ends the chapter on biomass.